Bam, Mr. True. So you've been learning the definition of a derivative and finding slopes of tangent lines and derivatives of functions using that definition. You might have noticed, though, that the problems were a little bit on the long side and a little bit tedious. You might have also noticed that some of your answers, a lot of your answers, looked, well, you can see a pattern with how your answers looked compared to the original function. And then you started thinking, man, why am I doing all this work? I can see the answer. Maybe you had some friends help you with homework and they're like, dude, this is like, you're taking up a half a page of work and something I can just, see the answer to. So let's start, now that we've really solidified that we do understand that derivative is slope, we use derivatives to be able to find the slope of a curve along any given point, assuming that tangent line's not vertical or there's a sharp bend there. Let's start talking about the basic differentiation rules. The constant rule. The derivative with respect to x of a constant is equal to c. And let's not forget the derivative will give us the slope of a curve or a linear function for that matter. And f of x equals c, like y equals 4, is a horizontal line. Well, horizontal lines have a slope of 0. So thus, the derivative of a constant is equal to 0 because derivatives are basically slope. Power rule. If n is a rational number, then, like 2/3 or 1/2, a rational function, number, could be 5 too, but anyway, then the exponent, well, I want to stop. The exponent can't be like square root of 7, okay? So as long as n is a rational number, then the function f of x equals x to the n power is differentiable. And when you find the derivative with respect to x of x to the n power, it's equal to n times x to the n minus 1. So we're going to do some examples on the next screen, but we're going to take that power, we're going to drop it down out front and have it become a multiplication and reduce the exponent that we just pulled that from by a value of 1. For f to be differentiable at x equals 0, n must be a number such that x raised to the n minus 1 is defined on an interval containing 0. We had an issue with this when my video where we tried to use the definition of a derivative to find the slope of a vertical tangent line. My function that I used in that example was f of x equals x to the 1/5 power. This is defined at 0. But when I go to find the derivative, and this is the derivative of the original function, this derivative is undefined at 0. So sometimes you'll have an issue there. So while I found a derivative of my original function, I can't find the derivative or take the derivative at the exact value of 0. And we had to deal with finding a left-right limit to make sure or come to the conclusion that our tangent line was indeed vertical. So that's the first two rules we're going to learn in this video. Let's do a couple of examples and, let's see what they look like. Alright, so here's our three examples. F of x is equal to x to the 5th. So, f prime of x, or what will be the derivative of x, f of x, is equal to the derivative with respect to x of x to the 5th. Okay, so using the power rule, what that means is we're going to, or how that's going to allow us to work this out, we're going to take that exponent, drop it down up front, so it's going to be 5x, and then it's to the n minus 1 power, so 5 minus 1, or 5x to the 4th. And again, the derivative, which this is now f prime of x, let me just write that as a summary statement. This equation again will describe or give you the slope of that original function at any particular given value of x if you so desire. Here we have g of x is equal to the 4th root of x, and that can be rewritten as g of x is equal to x to the, now this x has a power of 1, so we're going to have x to the 1/4 power. You really want to have these written, you want to get rid of those radical notations, or at least I prefer, and write them in with rational exponents. So this is, we can see now that this problem here is really the same as the original problem, x to the 5th. It's just that I have a rational power. So I'm going to take that n, that value of n, that 1/4, pull it down up front after I write my derivative notation. So g prime of x is equal to the derivative with respect to x of x to the 1/4 power. and that is 1/4 x, and then we're going to have to subtract this. So we have 1/4 minus 1, which we need a common denominator, so we're going to make that 1 equal to 4/4 and get 1/4 x to the negative 3/4 power. Alrighty, well, we don't usually want to leave negative exponents, so I'm going to take that x to the negative 3/4 and drop it to the bottom and have g prime of x is equal to 1/4, and taking that x and dropping it to the bottom, we get 1/4x to the 3/4 power. And that's a perfect way to leave your answer. However, if you're feeling like you started with a radical and you'd like to end with a radical, let's not forget that when you have a rational exponent, the top number is power and the bottom number is the root. So you could rewrite this as 1/4 times the 4th root of x to the 3rd power. I'm going to erase that and leave it in my original format here, but that is how you go from a rational exponent into notation with radical symbols. Alrighty, our third example is h of x is equal to 1/x. Again, I'm going to do just the opposite I did over here, where I had a negative exponent, so I moved my base to the denominator. Here, I don't really want to, I'm not comfortable, we haven't learned the quotient rule yet, that allow me to find the derivative of this equation in this format. So I'm going to rewrite it as h of x is equal to x to the negative 1 power. Now that I have it written in that format where I can use the power rule, it is equal to negative 1, h prime of x is equal to, and I'm going to skip the derivative with respect to x notation here and just write the answer. We're going to take negative 1, pull it out front, and have negative 1x, and then we're going to have the original exponent minus 1, so it's going to be h, not f, but h prime of x is equal to negative x to the negative 2 power, because negative 1 minus 1 is negative 2. Well, again, we're not usually very happy with negative exponents, so we can rewrite this as h prime of x, or the derivative of h, is equal to negative 1 over x squared. Okay, now that I have my third and last example I'm going to do for this particular panel, let's just take it one step further and say, well, what is the slope of the function h of x, or the function h, at negative 2? Well, my original function here, I'm not asking you to find the slope at a point which is undefined, because this is undefined at 0. This function is defined at negative 2, and actually it's going to be continuous at that point as well. So the slope there is equal to, well, let's just take the derivative, plug in the value of negative 2, and see what we get. Well, negative 2 squared is negative 2 times negative 2, which is positive 4. And we get a slope of negative 1/4. So let's look at a couple more properties. Bye! Next rule, the constant multiple rule. It says if f is differentiable, is a differentiable function, and c is a real number, then c times f is also differentiable. And it says the derivative with respect to x of c times a function is equal to c times the derivative, that's what that prime means, of the function. So here's our three examples. We have y equals 4x to the third, so you don't think you always have to use function notation. And y prime is going to be equal to the derivative with respect to x, of 4x to the third. Well, the 4 is a constant multiple, so this rule says that I can take that constant and pull it out front, so it's equal to 4 times the derivative with respect to x of x cubed. Okay, well now I've got a nice little basic power setting here, and so I'm taking the derivative of x cubed, which is going to be 4 times, take the 3, drop it down up front, and reduce that exponent by 1. So it's going to be 3 x squared. And then of course, now you can take the 4 and put it back in, and you get the y prime, or the derivative of y, is equal to 12x squared. Next example, we have 4 times the square root of x. So f prime of x is equal to the derivative with respect to x of 4 square root of x. Now, I'm going to take that square root out because it's not written as a power function. I'm not exactly sure what I'm supposed to do with the square root. Well, again, the x has a power of 1, and it's a square root. There's nothing in the index, so this is actually x to the 1/2 power. There, now we go. Now we can do it. Take the 4 out, and we get 4 times the derivative with respect to x of x to the 1/2 power. We can bring that 1/2 out and get 4 times 1/2 x, and when we do with the power rule, we have to reduce this by 1, so 1/2 minus 1 is negative 1/2, and that means that we're going to have, well, 4, and it's 4, over 1, so we're going to do 4 times 1 is equal to 4. Actually, I could take the 4 and reduce it, huh? That's kind of silly. How about we just say that 4 times 1/2 is 2? And we have 2, well, it's 2x to the negative 1/2 power. But again, we don't like to leave negative exponents. So I'm going to go ahead and take that negative 1/2 power and move the base down to the base of x to the denominator of what is now going to be a fraction, and have 2 over x to the 1/2 power, and that is equal to f prime of x, or the derivative of x, is equal to 2 divided by x to the 1/2 power, or you can write that as 2 over the square root of x, and that's the derivative of 4 square root of x. Over here we got, it could potentially look a lot nastier, maybe a little bit scary, but let's see here. We have f of x is equal to 3 over 4 times the cube root of x squared. So I want to pull this x out and give it its own little fraction and write 3 over 4 as a multiple, since that's what we're dealing with here. So this is going to be equal to 3 over 4 times 1 over the third root of x squared. Or that's going to be not the cube root of x squared, but x to the 2/3 power. Now, I still can't find the derivative here because this is not written in the setting of the power setting that we've been dealing with. It's actually division, and we don't know the quotient rule yet, nor would it be a great choice here because of it would make things a bit more complex. So we have f of x is equal to 3 3/4 times x to the negative 2/3. And again, I'm doing that separate, so I have the constant, and then I have a base with a power on it. So f prime of x is equal to 3/4 times, now let's go ahead and shorten this notation up a little bit. We want to take the derivative of x to the negative 2/3 power. So I'm going to bring the negative 2/3 out. And we're going to have the x. I need to reduce this by a value of 1. So let's see here. Negative 2/3 minus 1. We need a common denominator. So make that 3 over 3. And 2 minus 3 is negative 5. Or negative 2 minus 3 is negative 5. So we have negative 5/3 after we reduce that exponent by 1, which is the power rule says we need to. Well, what do we have to do now? Well, the 3's, of course, are going to cancel out, and the negative 2 and the 4 are going to cancel as well and reduce to 1/2. So in the numerator, we're just going to have a negative 1. So f prime of x, or the derivative of x, is equal to negative 1, over, numerically, or with the cancellation, I was just left with a 2. And then x to the 5/3, to get rid of the negative exponent, let's drop that base down to the denominator and have negative 1 over 2 times x to the 5/3 power. And that is the end of this example. Let's go on to the next rule, which is going to be the sum and difference rules. Bam! And here we have the last rule in the video, the sum and difference rules. And along with the other properties we just looked at, or rules we just looked at, the power and the constant multiple rule, we can just now look at these equations, these functions, and pretty much just write the derivative pretty much just like that. So if we have f of x is equal to x to the 4th minus 2x to the 3rd plus 5, that is going to be equal to, and maybe I should actually read what the sum and difference rule said, the derivative with respect to x of f of x plus or minus g of x, so this is our collection of terms being added or subtracted together, is equal to f prime of x plus g prime of x. So basically we can just find the derivative of each of our individual terms and just put them together, or allow that to be our new function, derivative function. So x to the 4th, the derivative of x to the 4th we now know is going to be 4x to the 3rd, negative 2x to the 3rd. Well, that's going to be negative 2, our constant multiple, times the derivative of x to the 3rd is going to be 3x squared. And then the 5 is a constant, and the derivative of a constant is equal to 0. So ultimately, f prime of x here is going to be 4x to the 3rd minus 6x squared, and that's it. Let me just make sure I didn't say something silly. And good. So now we have f of x is equal to 2x to the 3/2 power plus x to the 1/2. So the same question, only rational exponents possibly to make this question a little bit more difficult. So f prime of x is equal to 2 times the derivative of x to the 3/2, which is going to be 3/2 x. Reduce this by 1, so we're going to subtract it by 2 over 2 and get 1/2 plus, take this exponent, drop it out, so we're going to have 1/2. And then x, 1/2 minus 1, 1/2 minus 2 over 2 is going to be negative 1/2. So ultimately we have f prime of x is equal to 2 times 3/2 is going to be, well, the 2 is going to cancel, so we have 3x to the 1/2 power plus, well, let's see, the 1 over 2, and we're going to take this base, this x with the exponent of negative 1/2 and move it down to the base and have 2 times x to the 1/2 power. And that's perfect unless you want to write it in radical notation for some reason, and that would be 3 times the square root of x plus 1 over 2 square root of x. And there's no need to, we're not going to rationalize this and find common denominators. Really, this is a perfect answer for our derivative, or f prime of x. Now here, we have f of x is equal to x to the 5th plus 3x to the 3rd minus 2 over x squared. This cannot be, and with our skill levels right now, we cannot find the derivative of this function in this format. This would require the quotient rule. So unless we can break this apart in individual terms, we are going to have an issue here. But we can. Remember, when we have, or when we're adding fractions, like say 2/3 plus 4/3. When you add fractions, you only add the tops. You don't add the denominators. This is not 6 over 6. This is 6, 2 plus 4, 6 over our common denominator of 3. So when you add fractions, you just basically copy the common denominator that's in each of those fractions, hopefully, if you're doing it correctly. So what does that mean? That means that I can do just the reverse here. I have a term over x plus 2 plus another term over x plus 2 minus another term over x minus, over x, was I saying the wrong thing? That's x squared in the denominator. So we're going to pull this apart into separate terms, re-simplify, and get it to look like these first two examples, and then we can apply the sum and difference rule along with the constant multiple rule and the power rule. So we have f of x is equal to x to the fifth over x squared plus 3x to the third over x squared minus 2 over x squared, and that's going to be equal to f of x is equal to, now when you divide like bases you subtract the exponent, so we have x to the third plus, divide like bases, subtract the exponent, so we have 3x, and then this is going to be minus 2. I need to get that x out of the denominator because then again I don't want to be left with another quotient because I don't know how to find the derivative of a quotient yet. So we're going to write that as negative 2 x to the negative 2 power. And now this is really just like these first two examples. We're going to find the derivative of each term separately, and the derivative, the final answer is just the sum of all those individual derivatives. So f prime of x, or the derivative of x, with respect to x is equal to, take this 3, drop it down, 3x squared plus, this has an exponent of 1, so when I drop that down I'm going to have 3 times x to the 0 power because 1 minus 1 is 0, and anything to the 0 power is 1. And when we multiply by 1, nothing changes. So I don't really need this x to the 0. I'm just trying to show you where the x went because it's about to disappear. So the derivative of 3x is simply just 3 because the x becomes x to the 0 power. Now we have minus 2. Okay, now let's take the derivative, that's the constant multiple. Let's take the derivative of x to the negative 2. Negative 2 out front, so negative 2x. Reduce that exponent by 1, and negative 2 minus 1 is negative 3. Clean it up, and we have the derivative of f of x, or f prime of x, is equal to 3x squared plus 3. Let's see here. Negative 2 times negative 2 is positive 4. Now, you might be wondering why I'm doing negative 2 times negative 2. The only thing with the negative exponent is the x. So all of 2x to the third is not going to drop down to the denominator to get rid of my negative exponent, just the x. So it is negative 2 times negative 2 is 4. And now to write the x so it does not have a negative exponent, we'll drop that down and have it as plus 4 over x to the third power. I'm Mr. True. That's my last example. Where's my remote? Oh, there it is. Go do your homework. Go take some derivatives, man.